Benjamin asked us to do a high five between the talks, but I don't know if we'll do that. Can you hear me okay? All right. No? Pull this down. Is that better? All right. Okay. So, first of all, I'd like to give credit and thanks to Peter Goodwin, who gave us the description that we adopted as our title here. He called our project in a prior meeting the CASCaDE Journey, and we thought that was very apt. It's definitely been a journey. And it's a journey in progress. This is work in progress we're going to talk about. But what Lisa and I are going to try to do here is just give you an overview of the project, present a couple of examples of where we're going in terms of products of this integrated modeling approach that we're doing, and present some of the lessons that we feel we've learned over the course of the project and some of the elements that we felt it took to make a project like this happen. So, excuse me, the main question that's motivated this project is, how is the Bay Delta ecosystem likely to respond to big changes, changes that are likely to have significant impacts, like over the long term, climate change and its many manifestations in this system, and also over relatively shorter terms, infrastructure change. And in our case, we're considering two different scenarios of infrastructure change, both of these in the context of climate change. Multiple levee failures, multiple flooded islands, which most of you are familiar with as a real possibility, even potentially a likelihood in this system, and alternative conveyance. Generically, just the notion of some kind of infrastructure to at least partially bypass the delta as a conduit for freshwater transport from north to south. So this is just basically how the project works, and it gives you a sense of the geographic scope, the range of geographic scopes contained in the project. We start, of course, with global climate models. Our team members at the Scripps Institution for Oceanography have selected a subset of the current round of global climate models in the current assessment report that do a pretty good job, a relatively good job of representing climate variability over the Eastern Pacific and over California. And they downscale the output from these models to a grid over California. And this in turn drives a set of watershed models. So this includes hydrologic model of the unimpaired hydrology, which in turn drives an operations model. And also there's a water temperature model and a valley sediment transport model. And ultimately, those provide the upstream boundary conditions for the estuarine models. The global climate models are also used to directly drive the estuarine model through meteorology, and also as a product of global climate model outputs, again developed at Scripps, hourly water levels for these 100-year-long scenarios of climate change. And I should say, one of the features of our project is that we're not just parameterizing climate change effects with one model and then altering historical inputs accordingly to drive the next model. We're actually running through day by day, corresponding directly to the climate model outputs. So this really is a daily time step, Sierra and actually beyond to the Golden Gate and a little bit beyond modeling setup. This is a more detailed look at how the project works. I'm not going to go into this in a lot of detail, but I wanted to present it as to give you a sense of the disciplinary scope here. There's a wide range of disciplines that, of course, we need to try to address what the impacts on the ecosystem are. So this project is integrating across a range of disciplines, a range of spatial scales, and across the climate, atmosphere, watershed, estuary, ocean system, and across multiple influences as well, the climate influence and the internal changes represented by the infrastructure changes. I do want to highlight, does this mouse show up? No, I guess not. I want to highlight this shaded region behind several of these components that's titled Delft 3DFM Framework. This represents a modeling framework that we've developed in our project that contains several of these components, the ones represented in front of the shaded region here. And when I say framework, I mean the core hydrodynamic model, which I'll talk about in a second, and a set of ancillary tools that are used to apply the hydrodynamic model output to study the impacts on other different components of the ecosystem. And the core hydrodynamic model is, Deltares has been mentioned a lot here today, and this is something we worked with Deltares to develop and apply to this system. This is a relatively new model. The new feature over previous Deltares models is a new hybrid grid. I'm not going to go into the details, but it allows different types of grid cells to be applied in where they're appropriate for open water versus sinuous channels in the delta, and allows those grid cells to interface as well. And we've worked with them to help debug that and apply it to this system. The really essential aspect of this model for us is the fact that in the context of this modeling framework, it allows us to implement and drive all these quantities here. And the benefits of that are, for the ones especially that are contained within the hydrodynamic model, it allows real-time feedbacks. This provides us a more robust representation of the response of the system than having separate models that just exchange data files after they've run. And also, by having all these within one modeling framework, it really, I hate to use this terminology, but it really streamlines our workflow. These models and tools are meant to talk to one another, and makes it a lot easier to transfer the data from one to the next, and makes possible a range of analyses we couldn't have done otherwise. It's also, there are a lot of modules that have been developed for this system, many of which we haven't applied, that we would like to apply to this system. These include submerged aquatic vegetation, which plays a key role in this system, contaminants, which are part of our project but are not currently under this framework, and importantly, nutrients. And Lisa's going to talk a little bit about efforts to ultimately develop a nutrient model. So that's a quick summary of our project. I just want to hit a few practical lessons that we've learned. One is, that kind of hydrodynamic model is very computationally demanding. Even on supercomputers, we're not going to be able to run the full 100 years through it. We're going to have to select subsets of the full climate scenarios. We'll have great spatial coverage on those scenarios, but not full temporal coverage when it comes to running the hydrodynamic model. But one thing we've learned actually pretty early in the project is that it's very useful to develop simpler empirical statistical models at various points throughout the system that can be used to fill in the temporal gaps. This can be empirical, or it can be based on parameterizing the results of shorter runs of these more complex models. And this is a really useful way to fill in the gaps. And in the case, which I think Steve cited, of Wayne Wagner and Mark Stacy, this allowed us ultimately to look at evolution of delta temperatures and fish survival in the projections. This may seem obvious, but the elements in the project must communicate regularly. There are a whole slew of questions that have to be resolved where you have to understand what the task downstream of you need from you in order to define the task you're trying to accomplish. And these meetings are also really important because we're all kind of speaking different languages at first in our different disciplines, and it takes kind of repeated exposure to some of the same concepts to start to understand what each other are talking about and to develop a working cross-disciplinary understanding and language. And this is almost a precursor to really answering these questions. You can build delays into your project, but especially when you're using cutting-edge models and new data like we're using with the current round of global climate model data, there are going to be unanticipated delays. So it's really important for the downstream tasks to be flexible and creative, try to build in products that are relevant but don't necessarily depend on the upstream data, and also just to be ready to hit the ground running when you do get the data. And lastly, this has been mentioned in various forms a couple of times, but the output from one model doesn't necessarily speak to the next model, and you have to do a lot of transformation of inputs. This is easy to overlook, but when it actually has come to us having to do this, it can be very time-consuming. It really helps to have people on the project who are competent coders and are very familiar with different types of data sets and also with the overall needs of the project. and that can really speed things up. And one place that this has actually become an issue is in producing some of the synthesis products of the integrated modeling, and that's what Lisa's going to talk about next.
So picking up on this idea of data translation between different models, one example of where this has been a challenge that was recently resolved in our project is with the work that we're doing with a software called Habitat. This is another piece of software that Deltares develops, and it looks a lot like some of the stuff Steve Brandt just showed. The idea of Habitat is to produce habitat suitability maps for particular species. Even though this is a Deltares product and we're using other Deltares models, Habitat was not automatically equipped to receive data from or model outputs from our upstream models, especially these brand new flexible mesh versions of the Deltares hydrodynamic and water quality models. So this was a linkage gap between models that had to be solved, and Deltares built a new tool to perform that linkage for us and recently delivered that to us and basically customized it for us and for our needs. So now we're off to the races. So that was, it's just these are necessary delays, these are things you run into, and you need time to deal with them. So let me just tell you a little bit about Habitat. It, as I said, produces habitat suitability maps for particular species of interest. This is one example of how we're integrating in CASCaDE. To produce those suitability maps, it takes in two different kinds of inputs. It takes in maps of environmental parameters, which can be either derived from data, from measurements, or they can come from other models. And these can be things like maps of salinity, temperature, DO, what have you. And then these species response curves, also called HSI curves, habitat suitability index curves, convey, in my simple-minded engineer description of this, roughly the presence-absence of your species of interest as a function of those environmental parameters for which you are inputting those maps. And so Habitat takes all of this stuff in, mushes it together, does some mathematical magic, and out pops these habitat suitability maps for the time periods for which you're providing maps of your environment. So I have a couple early examples from our project that are pretty much a proof of concept. The first one is for Corbicula fluminea, the freshwater exotic clam that's so important in our system because it's a really critical limiter of primary production. And this is work that Jan Thompson is doing for CASCaDE. In this example, she's looking at Corbicula habitat as a function of water depth, salinity, and temperature. She's using a mix of model inputs from our hydrodynamic model that Rose Marder, our postdoc, generated. And the temperature map is, in this case, it's based on measurements. These are habitat suitability curves that Jan derived based on more than 20 years of data in this system. And here, for those inputs, is the habitat suitability map for Corbicula on a scale of 0 to 1, 0 meaning you're probably not going to find any clams there. As you get closer to 1, this is really good, at least physical habitat for this clam. And even though this was kind of a first cut at this, Jan is saying this is actually really reasonable. The highest values, those lavender areas, are actually where we tend to find lots of Corbicula in our system. So this is looking really, really promising. Here's another preliminary example for delta smelt. This is from Larry Brown and Marissa Wolf, where they for this early try at this, they've used input maps that are measurement-based from the fall midwater trawl. These are their HSI curves that they've generated based on over almost 50 years of data in our system. And here are their habitat suitability maps for Delta smelt for 2 different years that they did this. 2014, obviously a drought year. 2011, the last wet year that we've had. And you can see, especially if you focus in on Suisun Bay, there in the middle, pretty big difference between years. In 2011, the wet year, all of Suisun Bay looked really like good habitat for Delta smelt, at least from the perspective of these physical habitat variables. And that habitat was much more limited in 2014 under the drought conditions. Again, these are early tries at this, but Larry's saying from a fish guy's perspective, they're looking actually quite reasonable. So where is this habitat-based work going? Jan and Larry and their teams are going to be using this software to explore how habitat for a whole range of species of fish and 2 bivalves in our system, how that habitat moves, how it shrinks, how it increases as a function of different drivers of change, like climate change, infrastructure change. They're going to be able to compare seasons and hydrologic regimes early in the century to late in the century. And the input maps will all come from the upstream models, the hydrodynamic models and the water quality models. This new tool, this intermediate linkage tool that Deltara's provided for us, is going to allow Jan and Larry to do user-specified stats on those maps and then input those to habitat. Okay, so those were a couple examples of how we're doing some integration on CASCaDE. I'm going to add a couple more lessons, some big picture lessons to what Noah already shared. One thing we've learned is that for R&D heavy projects, especially projects linking lots of models and using new models or radically new versions of models, double your time estimates for how long this is going to take. One reason for that is that a major change in one of your upstream models will probably require adaptation for the other downstream models. For a project to be able to absorb those delays, long-term sustained funding is necessary to keep things going. We were asked to address funding. This is for our most recent phase of CASCaDE. Little more than 2/3 was USGS. We got substantial funding from the Delta Science Program, and we were really fortunate this last year to receive some key funding from SFEI. So I want to say a few words about what made CASCaDE possible. We built this on decades of data throughout the system, decades of research, a great team of people who really like working together and who know the system well, and seed funding to get us all working together at the same time on the same thing and keeping the project going in the long term. This has clearly been a big investment, and we're really happy that what we're building now will continue to be used in the future. One example is with the SFEI-led nutrient management strategy. In addition, Deltares has initiated what Carl described earlier, this San Francisco Bay Delta community model. This is a screenshot of the website. You can now download the 2D flexible mesh hydrodynamic model from this website. And all of our stuff, the software, our configuration files, our grids, et cetera, are all going to end up here for everybody to use. So we're really happy that the tools and capabilities that we're building are not going to end up in tar files and on hard drives and never see the light of day. We're putting them out there to hopefully facilitate further science by other teams and to build a community that can co-develop these tools into the future. So with that, I'd like to thank all of you for your attention and sticking with us, and thanks to the organizers for inviting us here today. Thanks.